Hello, good morning. Please let me know if you can hear me. I'm still trying to admit a few more people. Are you able to hear me? Yes, okay, thank you. Thank you. So the reason why it's taking long for many people to join is because I made it a requirement to go through the waiting room because I told you that you should not join the class anytime. Just join when it's time for the class, because when people started joining on Sunday at night, and I get emails and I don't like it. So I enabled waiting room, which means that only I can start it. Unfortunately, that costs us time. But if you were to promise that you won't be playing with the link, then it means that I open it up and people join during the class as and when they want. That aside, let us start. Today we are going to work on chapter 2. Let me just let you know that we will be studying with second years who are doing a course called Digital Logic, and it is essentially similar material. I'd never understood why it was taught separately, but we worked out with the class representatives a time that is good for everyone. So we'll be studying on Monday at 10 and on Wednesday at 10, I believe. Okay, if there is any, if I'm those two times are not right, the class representatives can let me know. Now, I think one of the class might have an issue on Wednesday where they have another class, but that's okay. They can leave the class. Is it at 10 or 11? I don't know. We'll figure it out. But the class who are engaged can leave the class even if I'm still teaching. I don't have a problem. Okay, so today we are going to look at number systems and codes, and I don't believe that these are any new to you. So I'll go through them very fast, and I'll be giving you some examples. So please, or some things to do. So please have a pen and paper so that you can get involved. The codes and number systems we are talking about here really are the ones that allow us to count. So the one we are most familiar with is the decimal system, but there are many other systems that we can use. For instance, we know that computer systems use a binary system, yet there are some others. There are some other codes where we'll be looking at the hexadecimal code. We'll look at a code called BCD. There's also gray code, which we are not going to cover, but if you're interested, it's in the book. So we are going to be looking at how we convert from one to the other and back, and how we can count how to count in decimal. Everyone knows how to count in decimal, up to trillions if necessary. But we may not know, some of us particularly, how to we maybe haven't been exposed to a code like hex. Now, let us start the class. We are going to start with binary to decimal conversion. Since we already know what decimal is, has 10 numbers, which are 0 to 9, and we know how we combine them to count. Okay, so or to create bigger numbers. So that is not a problem. But if we want to convert something like binary to decimal, we use what we call the positional value system or approach. Example, which is 1, 1, 0, 1, 1. This is in base 2. We want it to be in decimal. So we said that when we are trying to convert to decimal, we multiply by the power, the positional weight of each of the bits. So clearly here, this we said is the low significant bit, and this is the most significant bit. So the most significant bit will have a larger weight, and the least significant bit will have a smaller weight. And really, the weight of the lowest significant bit is actually a 1. So we are going to multiply by 2 to the power 0. This one we multiply by 2 to the power 1. This by 2 to the power 2, and 2 to the power 3, and 2 to the power 4. So if you have a number of 10 bits, you know, like a binary number of 10 bits, the most significant bit will have a weight of 2 to the power 9, which is really 2 to the power n minus 1, where n is the number of bits. And the least significant bit will always have a weight of 1, which is 2 to the power 0. So what we do is that we multiply each of the bits with its weight and we sum up. So here it is 1 times 2 to the power 4, which is 16, plus 1 times 2 to the power 3, which is 8, plus 0 times 2 to the power 2, which is really 0, because if a number, its addition to the number to the conversion will really be 0. Plus 1 times 2 to the power 1, which is 2 plus 1. And this is 16, 24, 26, 27 to the base 10. So if you convert 2710, you should be able to get that. If we had a number like 1, 1, 1 in base 2, we want it in decimal, we would do essentially the same, 2 to the power 0, 2 to the power 1, and 2 to the power 2. And so 2 to the power 2 is 1 times 2 to the power 2 is 4, plus 1 times 2 to the power 1 is 2, plus 1 times 2 to the power 0 is 1, which is 7 base 10. So we know that 7 base 10, if we convert it to binary, we get 1, 1, 1. Okay. Now, I'm going to give you so this is one way of converting to decimal. We can also convert to decimal. No, this is decimal to binary. So I won't give you an example here because I think this is really easy, but let me just show you something that maybe you haven't come across. If we are doing 0, let's say this is decimal, this is binary. If my decimal is 0, my binary is going to be 0. If my binary will be 1. But what if my decimal is now 2? If my decimal 2, my binary should be something 1, 0, okay? Because we know that 1, 0 in binary, this is 2 to the power 1 and 2 to the power 0. So if we convert this, we are going to have 2 plus 0, which is 2. What if this was 3, 1, 1, where 1, 1 is 2 to the power 1 and 2 to the power 0, and so you can see that we get 3. If it is 4, 2 bits are no longer able to tell us the binary, because we have seen that 2 bits give us 3. If we have 4, we need more bits. In this case, we are going to have 1, 0, and 0. Where 1, 0, and 0, we have 2 to power 2, 2 to power 1, and 2 to power 0. And you can see that this is the one that is has a 1, and so we have 4. If it's a 5, we have 1, 0. Tables will be second nature to you. Like, understand, you don't need to think too hard what the code is, because you'll automatically know it. 1, 0, 1, that's 2 to power 0, and 2 to power 2, which is 4 plus 1, is 1, 1, 0, and 7 is 1, 1, 1. If you went to 8, 8 its greatest form. If you go to 8, it means now you need 8 bits, and it will be 1, 0, 0, 0. We looked at how you do. So let us move. I won't give you an example here because I think this is really basic. But let us look at how we can convert decimal to binary. This is and okay, I'm saying I have 100 people. I thought I would have more, but that's okay. So combinations of numbers that are powers of 2, and we start with the greatest. So we know that 45 is equal to a large number that is a power of 2, 32. Okay. Ideally, we should add 16, but if we add 16 to 32, we will go beyond 45. So we jump 16. Okay. Then we go to, from 16, we go to 8. Okay. So if we add 8 to 32, we get 40. So that's okay. Now we add 4, and it will become 32 plus 8 plus 4 is 44. Plus, then we will add, we should add 2, but we don't. Okay, let me just, instead of, let me just add 16, you know, so these ones are not part of it. Then plus 2 to the power 0. You know, 45 is 32 plus 8, which is 40, 44, 45. Now we come and look through this. We know that this is 2 to the power 5. This is 2 to the power 4. This is 2 to the power 3, 2 to the power 2, 2 to the power 1, and 2 to the power 0. So then we can say that's a 1, okay, because it exists. This one 16 is not part of the sum, so we make it a 0. That exists. This one exists. That one does not exist, and that one exists. So use this way, we have converted 45 base 10 to base 2. And if we wanted to convert back, we know that we can have, this would be 2 to the power 5, as we say, 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0, which is 1 times 2 to the power 5, which is 32, plus 0. Okay, so that's 0. 1 plus 2 to the power 3, 2 to the power 3 is 8. 2 to the power 2 is 4. 2 to the power 1 is a 2, but times 0, that goes plus 1, which gives us our 45 to base 10. So as you can see, it is quite easy to convert back and forth, particularly using this positional value approach. Now I'm going to give you an example. I'm going to give you an example, and you can attempt. Let's look at another one, maybe just for effect. What if we have 27 base 10? We want it to go to binary. We know that 27 is equal to, we look at powers of 2 and we get the greatest that is below 27. In this case, it is 16, because from 16 you go to 30, which is greater than 27. The next one from 16 is 8. If we add 16 to it, we get 24. So that is part of it. After 8, we have 4. If we add 4 here, it will become 28, which is greater than 27. So that one is out. We can cancel it. In the book, they don't even add it, and you don't have to, but for teaching purposes, I want you to get all the information. Plus 2, okay, so 16 plus 8 is 24, plus 2 is 26, okay, plus 1 is 27, okay, so those stay. This is 2 to the power 4, 2 to the power 3, 2 to the power 2, 2 to the power 1, and 2 to the power 0. So you have a 1, 1, 0 here, because that does not exist, and the 1 and the 1 to base 2, which is similar to what we had earlier. So let me ask you to convert 87 base 10 to binary using this approach. Please take a minute to do this and let me know. You can put your answer in the chat. If you yes, a cell, I'm eliminating 2 and 16 because if I add them, I won't get 45. So you find numbers that are powers of 2 that give you a sum of the number in decimal. And so those ones which, when you sum them, they go beyond the number, you need to eliminate them. Obviously, I said another key information is that you start with the largest power of 2 that is smaller than the decimal number you've been given. So if it is 45, we can't just start at 16. We start at 30. Okay. And if we wanted the higher number than 32, it is 64, but now 64 is greater than 45. Okay, I'm seeing, so if you see this number, you don't have to, if that's the answer, you don't have to put it here. I'm seeing 1, 0, 1, 0, 1, 1, 1. That's 2. So I don't know, I've not done this, so let me do it. 87 will be 64 plus, if we add 32, it will go beyond 87. So we don't add 32. Let me cancel that. If we add 16, it takes us 80, which is below 87, so we add 16. If we add 8, now it becomes 88, which is greater. So we are going to cancel 8. But we are at 80, remember 64 plus 16 is 80, so we can add 4 to 84, we add 2, to 86, we add 1, and it gives us 88. And so this is a 1, that's a 0, and that's a 1, and another 0, and a triple 1, base 2. So that was correct for the guys who got that. Thank you. That is the correct answer. Okay. Let us continue. There is the other one, which is the repeated division approach. So for it, this is like primary school stuff. For it, you get the quotient. Okay, so if you have A over B, you have a quotient plus a remainder. And so you keep dividing the quotient, but under 2 is B is 2 basically. So you keep dividing the quotient by 2 until the quotient is 0, until Q is 0. You can see in this decision here, so you get your number, you divide by 2, you get a quotient and a remainder. And then you keep dividing until Q is 0. If Q is not 0, you go back and you do the same. If Q is 0, then you correct errors into the desired binary number. I'm going to show you how you do that. So let us do the same 45. So you get your 45, you divide it by 2. You are going to get 22, remainder 1. Then now this is your quotient. So you need to divide it again. 22 divided by 2 is equal to 11, remainder 1. And now 11, is it 11 remainder 0? Sorry, it is 11 remainder 0. 11 you again divide it by 2, you get that is 5 remainder 1. And then you have 5 divided by 2, you get 2 remainder 1. Then you get 2 divided by 2, which is 1 remainder 0. And still the quotient is 1. You need to make sure that it is 0. So you get 1 divided by 2. If you get 1 divided by 2, it is 0 remainder 1. And then you write your number starting from this remainder to the first remainder, which is 1 0 1 1 0 1. Is that what we got earlier? 1 0 1 1 0 1. Yeah, to base 2. Okay, I know that people keep jumping off. I don't know why. And unfortunately, now I cannot disable the, until we finish the class, I cannot disable the waiting room. But this, there are some people having trouble joining. That's why it's a pity. But I am going to remove that requirement. But please, 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 because it also disturbs me, I keep looking at, I keep looking at the waiting room to admit people, and it disturbs me. But please, 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 I'm going to remove that requirement. Do not join the link when we do not have a class. All right. Every time you join, I get an email and it fills up my inbox. So I think that is very clear. Let us do another small one. We know, for instance, that 16 base, okay. We know that 15 base 2 is base 10, sorry, is actually 1 1 1 1. Now 16 base 10, that means 16 cannot be represented by 4 bits. You need 5. So it's actually 1 0 0 0 and a 0. So let us convert 16 to base 2, and then I'll give you an example. 16 over 2 using this approach is 8 remainder 0. 8 over 2 is 4 remainder 0. 4 over 2 is 2 remainder 0. 2 over 2 is 1 remainder 0. And 1 over 2 is 0 remainder 1. And then we write our number from down going up, which is 1 0 0 0 0 as we expected. So now I'm going to give you a number. You convert for me 87 base 10 to binary using this approach, because at least we already did that, so we know the answer. Just take a minute and put your answer. But actually do it. Just because we know the answer doesn't mean you just put the answer. I would also like to, Harry? What is 21 minus? I hear some of you are playing music. I don't know why, but yeah, Joan, the same answer, but yeah, a couple of you have the answer. Well done. We all know the answer, but let's hope that you've actually. Remember, I think the key here is that the last step. People forget the quotient must be equal to 0, and usually the last number is 1. The last remainder is 1. It has to be because if the last remainder is 0, you cannot also have a quotient which is 0. Maybe if at this point you continue, then you know. But also these numbers do not start with a 0. Like the most significant bit should not be a 0 because it's meaningless. You know, even in decimal, if I have a number like 0, 1, 0, 0, if this is decimal, this is just 100. There is no need for me to put a 0 at this side. I think the other key that you must keep in mind is that when you are writing your number, you start from the last remainder upwards to the first one. Okay, thank you all. You got it. If you start writing your number from up going down, you're going to fail. All right. Let us move on. Yeah. So the counting range, if I'm looking at the counting range, if I'm looking at binary, I tell you that I have, yes. If I tell you that I have a binary number of 4 bits, what is going to be my counting range? The counting range will be 4 bits. 4 bits are made up of, the minimum number made up of 4 bits is 000, which is really 0 in a decimal. And the maximum number here is going to be everything 1111. So that then becomes my counting range. So if I have 4 bits, I can count numbers from 0 to 1111, which in fact in decimal is 0 to 15. All right. Now, generally, when I have n bits, I can count up to 2n minus 1. This is the largest number that I can count using n bits. So when n is 4, the maximum number, I should call this the maximum number that you can count to. If n is 4, my maximum number will be 2 to the power 4 minus 1, which is 15, not 16. 2 to the power 4 itself is 16. But we remember we start counting from 0. So it is 0 to 15, where this is the maximum number that I can count. And if I'm counting, if I have 8 bits, I can count from 0 to, let me say 6, because I can count from 0, which is 0, 0, 3, 4, 5, 6, to 1, 1, 1, 1, 1, 1. This is essentially 0, and I can assure that that is 63 in base 10. Not 64, but 63, which is really 2 to the power 6 minus 1, 2 to the power 6 is 64. So that means that if we are looking at those two numbers in A, the total range of decimal values that can be represented by 8 bits, I'm looking at 8 bits, which is 0 to 2 to the power 8 minus 1. 2 to the power 8 is 256, so it is 0 to 255 to the base of 10. Now, okay. Please, since we are studying online, and I'm sure you're doing online for all your classes, it's important that you find a solution to your network, be in a place where the network is good, because some of you keep dropping off and trying to join in again, which tells me that you don't have good network. So can you do B for me, this number here? Is my audio ahead of the video? The audio is ahead of the video. Yeah, it is possible that that's the case. I don't really know how to fix it. Unless I drop off and I come back on, but if I drop off, it might make me, for some people they are in sync. Yeah, just says they are in sync. Sometimes it is your network and not my issue actually. Yeah, for some students, everything is okay, so there's no need for me to change anything. It is probably because your video, your network is not good. Again, you should find a place where your network is really good, because this is serious. This is actually studying. We are studying. It's not a waste of time. So it's important that you optimize your connection. But if it is about this, the writing itself can lag by a couple of seconds, perhaps. That's okay. Because remember, as I write it, all this is, the video is heavier than audio, so it can lag a bit. But for most people, that's okay. Now, are you doing part B for me? Yeah, for Emmanuel, the counting range is, so for instance, if you want to count 100 things in decimal, you know that I'm going to count from, says in binary, this is how we do it. We count from 0 to 99. This is 100 different numbers, or 100 unique numbers. Just one moment. You can continue doing part B. Yeah, my computer is a bit slow. I can also now see. Right. Yeah, so in binary, if I want to count from, if I have 4 bits, the counting range will be basically 0, 0, those are 4 bits, to 1, 1, 1. It means in here from 0, this is equivalent to 0, that's 1. So I can say 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. All these are going to be unique numbers that use 4 bits. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. Then I go to the next number, which is 1, 0, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, no, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. So this is really 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But once we make everything 1, 1, then our 4 bits are represent those 4 bits, or the 16 options are finished. And so that means that with 4 bits, we can count from 0 to a number that is equivalent to 2n minus 1, which is 2 to the power 4 minus 1, which is 15, which is that. Okay, yeah, some people, we cannot have points. When we are looking at bits, we cannot say points. I like your answers. Just throw 14 bits. Yeah, that's correct. When you write bits, you leave a space. 14 and bits, you leave a space. You don't combine them. Somebody was intelligent enough to find the 13.6 bits, but that would be wrong because we cannot have a full bit. So we find a number of bits that is greater, like in this case, we are looking at, we are counting from 0 to 12,500. And so we want a number that, a number of bits that will count greater than that. If we count less than this, we are not able to count the full range. But we find a number that is greater than that. And so the guys who have done it actually already have the answer. So if we look at 2 to the power 13, I think, is that 8192? Okay. And 8192 is still less than 12,500. That is the right answer. Yeah, 8192. So since that one is less than this, we need to increase the number of bits. is 16,384, and this number is greater than 12,500. So we have found that we can use 14 bits to count from 0 to that. In fact, we can, using 16, 3, 8, basically 3, okay, because we would have to do 2 to the power n minus 1. So the counting range using 2 to the power 14 is not actually 84, but 83 here, right? Now, 12,500 is within this range. So that means we need to use 14 to count that. Obviously, 500, there are still possibilities, and that's okay. We can ignore those possibilities once we have counted to the point that we want. But you're never going to use 13 bits to count up to 12,500 because they only stop at 8,191, not 92. Now, what if we used 15? What is wrong with using 15? What if we used 15 bits, because they will also 16 or 20 or 100, because they will also clearly give us at least 12,500, right? It is a problem. Obviously, it is going to work. If we use 16, it will work. Okay. We don't have to use 15 because 14 can work. The fewer the number, if in your memory you have data that is useless, now what is that to you? And so we usually use the minimum number of bits that we require actually to perform. Use the more bits, it would still work, but that is a waste of memory. I think somebody, Musa, is asking a radix point. I think a radix point, I don't remember my primary math, but I think a radix point, there are these sorts of number separators. We don't really have to care about that one here. All right. Okay, so that's how we reach 14 bits. If we use 15 bits, there will be 2 zeros prior to a 1. Okay, I've not understood that, but let me give you another example. What if we wanted to count up to 1 million? Okay, I have 1 million things. I want to count them uniquely. Let's say that the population of, you are doing the population of Uganda. Let's assume that the population of Uganda or Kampala is 1 million people, and you want to give it to identify each person using a unique binary code. How many bits do you need to combine to be able to count the people in Kampala if we assume there are 1 million people? Okay, that's 20 bits. Yeah, I agree. A same way, yeah, you can use, I think with these things, methods are, you can use different methods to reach your answer, but I don't think there is a method that is, basically what the guys are doing who are doing this is that you get a power and you keep trying until you reach the powers, the 2 points where your number that you're looking for is between those 2 powers. So you see something like 2 to the power, I'm sure people looked at 2 to the power 19 and saw that 1 million is greater than this. Then they looked at 2 to the power 20 and so that 1 million is actually less than that. In fact, 2 to the power 20 is not 1 million. It is 1 million plus a few things. So that means that you have to take the upper side to be able to count up to at least 1 million, much as that range can count to even more. So the reason why I brought 1 million is because people say that when you have 1 million bits, you have what we call a mega, an MB, a megabit or something like that. But in fact, this is wrong because a megabit is actually 2 to the power 20, and 2 to the power 20 is not 1 million. It is something greater. It's similar to if you have 1 KB, it is not equal to 1,000 bits. It is actually 1024 bits. So let's carry on. Okay. Yeah, as I say, there are so many ways that you can count the that you can reach the answer, but the one I give you, you don't have to use the one I give you, but there's somebody who needs to mute themselves. Okay. So the hexadecimal system uses decimal 16. It is by having decimal 16, just like we have decimal 2 for binary, meaning there are 2 numbers, decimal 10 for decimal, base 10 for decimal system, meaning there are 10 numbers. If we have base 16, it means we have 16 unique numbers. And for hexadecimal, the numbers are, it has the decimal numbers 0, 1, 2, 3, 14, 4, 5, 6, 7, 8, 9. And after 9, it goes to, it uses letters A, B, C, D, E, F. So in decimal, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then here for decimal, this is 10, 11, 12, 13, 14, 15. These are 16 numbers for this for hexa. So hexadecimal uses these numbers and then these numbers. And we already know the binary equivalent because we did the table from 0 to 15 to 15 once again. So you can create a table that shows everything. Now, when we are converting to 16 to decimal, to whatever we are converting back and forth, we are going to look at this. But you can see here that we have a positional value system where it is 16 to the power 4, 3, 2, 1, and so on. And if we have a point here, then the positional value system here becomes 16 to the power -1, -2, -3, -4, as we saw in chapter 1 for binary. So basically, it means that if we have, if we were looking at binary, for binary 10, for decimal 10, binary would be, okay, we know that 9, no, let's start, let's do this, okay, let's do this. Decimal, hex, and binary. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. The hex is obviously going to be the same, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now the binary, because we know that we are looking at 16 unique values, it is 0, 0, 0, 0. We have to use 4 bits, 0, 0, 0, 1. These ones you need to practice how to write them, how to follow from step to step. 0010, 0011, 0100, 0101, 0110, 0111. And for 8, it is 1000. For 9, it is 1001. Okay. Then we need to complete this. Okay, so decimal, from 9 we go to 10, 11, 12, 13, 14, and 15. And for hex, 10 is A, 11 is B, 12 is C, 13 is D, 14 is E, and 15 is F. And in decimal, the equivalent here is 1001, so 1010, 1011, 1100, 1101, 1110, and 1111. So this is a table that expresses the equivalence between decimal, hexadecimal, and binary. By the way, this is binary. Now, let us look at some conversions of hexadecimal. So how do we convert 356 base 16 to decimal? We do it the same way we did binary. We multiply each using its positional value. So this is 356. This is 3 times 16 to power. Obviously, this is going to be 16 to power 0, 16 to power 1, 16 to power 2 squared plus 5 times 16 to power 1 plus 6 times 16 to power 0. That's a 6. That is 80, and I don't know what that is. Okay, so and I think that is 768. And that gives me, please do the calculation to make sure that I'm not making a mistake. 768 plus 80 plus 6. 854 to the base of 10. Okay. All right. Let me see. Yeah, 854 to base 10. Thank you. If we are doing this one, it shouldn't confuse you. This is going to be 2 AF. This is base 16. So that's 2. No, that's 16 to power 0, 16 to power 1, 16 to power 2. And that gives us 2 times 16 squared plus A. Now, A, we need to remember it is equivalent to 10. Okay. So we say 10 times 16 to power 1 plus F. F is 15. Okay, as you can see, F is 15. 15 times 16 to power 0. And I don't know what you get, but please, while you are at it, also convert for me B 9 D C 16 to decimal. Right. Okay, somebody has given me 687, another one 672. 687 to base 10. Right. Is it 687 to base 10? Perhaps. Yeah, I'm seeing move 687, so maybe that's the call. Can you do this one? It would be a rather large number. I'm seeing 47580 base 10. I'm seeing that number a lot, so I think it's correct. Yes, thank you. If you have, yeah, that's okay. That's okay, really good, since you are all getting the same answer. Now, with decimal to hex, we use repeated division because now using the other approach is going to be a bit cumbersome. So here we use repeated division. We can get 423. Please mute yourselves. If you come into the, just mute. If you are muted, you just mute. This is 423. Now, when we were doing earlier the repeated division, we were converting decimal to binary, but now we are converting decimal to hexadecimal, sorry. So we need to use 423 to power divided by 16, not divided by 2. And we are going to get 26 remainder. Uh, 7, and then we go back, we divide 26 by 16, we are going to get 1. I think 1 remainder, 10, and 1 divided by 16, we are going to get 0, remainder 1, isn't it? So then we do yeah. Okay. And then we can write our hexagonal number. Just one moment. Yeah. Okay, so we know that 10 is A, the rest are written as they are. So we have 1, we write again from down, 1A, 7 to base 16. Can you do this one? And you tell me the answer? So you have 2 numbers to do. Yeah, D6 is correct. Is my screen covered? D6 is correct. So if you have got D6, that's okay. How is my screen covered? I don't understand. Okay. D6 is correct. If you have got D6, now you can do the other one. If you have got D6, it's correct. You don't have to type it in here. Harry?
Yes, sir. I wanted to find out, because when we started with 4 to 3, we said we use the repeated division. But
yes.
when we divided that 4 to 3 by 16, we get 26.43. And if we round it off, that would be 0.5, right?
We round off to the, you don't round off when you are looking for the remainder. You take the full number as it is, and then the fraction, you multiply it by 16 to get the remainder. You get it?
Okay,
so
yeah,
like 40,
I get it.
You get it. So we don't round off. We take the full number and use the fraction to get the remainder.
Then the other question.
Yeah.
Is this the formats they use on MAC addresses and IPs?
Yes. The IP addresses tend to be expressed in hexadecimal, and so for you on the surface you see a hexadecimal number or some kind of decimal number, but behind it is actually binary. So I'm going to be talking about sorry, I dropped off, I believe, for a moment. Sometimes when I'm tethering on my phone, that happens, but I hope you can hear me. And also you can see the shared screen. Did we get an answer for that? I see 593. Okay, base 16. Okay, so since everyone has that, so we would have 1,427 over 16. We get a quotient and a remainder. And then we take that back, that quotient divided by 16 again, and so on and so forth. And then we measure or write our number from down upwards. Right. Now, what about hex to binary conversion? This is very easy, actually. You just get each hex digit and write its binary equivalent. So you can see like 9, F2, we know that 9 is 1001, okay? For F is the last digit or equivalent to 15. So that is a 1111, and 2 is clearly 0011. And so your hex equivalent in binary is just you get each hex number and you write its binary equivalent, and that's enough. Another way you could do this is first convert the hex digit into decimal, and then from decimal you can convert it to binary. But why do all that when this is very clear? Let us look at BA6. So we want to see if this is equal to that. we can look at the first 4 digits on this side. So usually when you are doing this, you should start looking in that direction. But actually, usually this will be okay. It will be an equal number of digits. So we're looking at 0, 1, 1, 0, okay? Then that's it. And those are the other 4. We are looking at 1, 0, 1, 0. And then also 1, 0. Remember, this was 6, okay, in decimal. That one is 1010, which is 10, okay, that's 10, and 10 we know is A. And then 1011 is the number after this, which is B. So you remember our table here. B is 1011, and A is 1010. So that is as simple as that. There is nothing hidden. I could make up a code and ask you, let me make up a code and ask you to tell me its binary equivalent. Okay, let me make up a, we already saw, let's say a code like D7F base 16 to binary. So D, we get its binary equivalent. 7, we know 7 is 0, 1, 1, 1, and F is 1, 1, 1, 1. D, which is 13, is 1, 1, 0, 1, 1, 1, 0, 1. So that is your binary equivalent of D7F. I don't think that we need to dwell too much on that. Let us look at binary to hex. What if it's binary to hex? That for, so it's really the opposite. You group it into bits of bits per hex value. How about if the number is involving decimal points? If my network is breaking, it's a problem, and we may have to. If the number has, for conversions involving decimal points, I don't really dwell on them. I don't bother with them. But if you are interested, there's a lot of things. There's a lot of, so you can go and read about those on your own. But I will probably not ask them in an exam. So create 4 groups. No, create groups of 4 bits, but start from right side, which is the low significant bit, and then another 4 and another 4. Now these are 2 clearly, but we add zeros to make it 4. 0110 is 6. 1010 is A, and 0011 is 5, I think. No, it is 3. Okay, it is 3. So you have 3A6 to power 10. You're looking at this. You're looking at 4 bits, another 4, and another 4, where this is, so this is 1111, which is F. 0101 is 5, okay, because you see 2 to power 2 plus 2 to power 0, which is 1. So that gives you 5. And then 0, you have a 1 alone, so it becomes 0001, which is a 1. So you have 1515F in the base of 6. So you can see that the conversion to binary and hexadecimal is very easy. The reason why hexadecimal is good for us humans is because instead of having a code of 64 bits, you're looking at a binary code of 64 bits, you can look at the equivalent of that in hexadecimal, in which case there would be 16 hexadecimal numbers, which is easier for you and me to read. Can you imagine reading a stream of 64 bits? It's just difficult. And so we use hexadecimal to easily convert between binary and hex, so that for us, we read the hexadecimal number and make sense of it, whereas the whereas the computer uses binary. So for the computer, it can use binary, but for us, we use hexadecimal. It is similar to how we insert information into a computer. You have a keyboard, and on your keyboard, you just see like a number, a letter, and so on. But really, every time you press, say, letter 1 or letter A or number 1, what the computer sees is its binary equivalent. So it's just like an interface for us to interact with these numbers in an easier way, being humans as we are. Okay. So they are saying that my network is bad, and I apologize for that. I am on a 2G connection, and so I have no clue. Can you still not hear me? Because I would rather stop the lecture. Okay. Please apologize. I apologize for that. I'm in a new place, so I'll try and change that. By the way, sometimes it's on your side, so that is the issue. I don't really know when it's my fault or not, but let's continue. So that is really the useful of hex, is that we use it to interact with the numbers that the computer understands, but that would be very difficult for us to understand. We have the idea of counting range in hex, but let's see how we count in hex. I have these two scenarios. Now we have 38, 38 if we were doing decimal, 38, 39. Now if we were in decimal, after 39 we would go to 40. In other words, you go back and increment this value in the ones position and take that back to 0 so that you can count through the range again. However, in hex, after 9, we still have A, B, C, D all the way to F. So you can see that we have to go from 39 to 3A, 3B, 3C, 3D, 3D until we finish the range for hex, which is F. At 3F, we go and increment the number in the ones position and then take that back to 0, which means 40, 41, 42. That means we are going to go on and reach 49. The moment we reach 49, we don't go to 50. We are going to go to 4A, 4B, all the way to 4F, after which we can go to 50. If you look at this one, it is 6F. Already we are at 6F, 8. 8, 9. Now at 9, we need to go to 6FA because for hex counting, we don't stop at 9. We stop at 9 during decimal counting. 6FA, FB, FC, FD, FE up to FF. Now, because we have 6F and F, these are already at their maximum. It means we need to go back to that value and increment it to 0 to 7, and then everything goes back to 0. Just like we count in decimal. It is also, by the way, in binary. It is the same. We just count to the end of the range and increment the next number either in the ones or tens position. Any number beyond F is you just go back. It's what we are doing now. You can see that when you go to beyond F, you in decimal. If you are to ask me a question, how do we count any number beyond 9? We just go. If it was 9, it means that it was 09. If we have a number beyond that, we increment this value and take this back to 0. So we know 10 is greater than 9. So you can always find ways of counting in hex the same way we count in decimal. Let us look at another example. This can actually be confusing for students. So what if I have F F6? It means I'll go to F7, FF8, okay, FF9, FF10, you know, 10 is A, FF11, which is B, FF12, which is C, FF13, which is D, FF14, which is E, and FF15, which is F. So I have FFF. What is my next number? So what will be my next number? Because now all these three digits or these three positions have reached their maximum value. So I can't increase this, I can't increase that, I can't increase that. So what will be my next position here? It will now, I have to increase the number of positions. So I go back, we would be assuming that there is a 0 here, much as we don't write it. So I make it 1, and then I restart everything at 0, 0. And then I will go maybe 1001, 1002, 1003. Eventually, you'll come back full circle and find yourself at FF, F, and F in these 4 positions, and then you can go to 1, 0, 0, 0, 0, and you continue counting. All right, let me thank somebody, the guys who got this. Yeah, a number of you got this. This shows that you are following Ham and Jethro and the rest. Great. So that is how we count in hex. I sometimes bring this in exams, so it is important that you try and understand. Now, we have a decimal number, 421. We want to convert it to a binary number by first converting it to decimal. Can we do it? So I've given you a decimal number, 421. Convert it to a binary number, but please first convert it to decimal. By first converting to hexadecimal.
Decimal. Binary hexadecimal. 4 to base 16. Binary.
Yeah. So you convert 421 to binary by first converting to hexadecimal. Because we know that once our number is in hex, it's really easy to convert to binary because it is direct conversion. Okay. Do we have some answers? Okay. So it is one. Fahad has too many numbers, so I don't know which is which. I really don't know. I see 1, 0. Oh, do it together. So 421 to 421 divided by 16. We are going to first convert to decimal. Is again 26. Remainder 5. 26 divided by 16 is equal to 1. One remainder equals that minus 1 times 16. Remainder 10. And 1 over 16 is 0, remainder 1. So we have 1, A, and 5. And to convert this into decimal, into binary, we have this, it is 0, 0, 0, 1. That is 1, 0, 1, 0. And that is 1, sorry. And that is 1, 0. It is 0, 1, 0, 1. Okay, yeah. That's 4 plus 1 is 5. So we end up with 1, 1, 0, 1. 1, 1, 0, 1, 0. Okay. And then 0, 1, 0, 1. Okay. There are 3 zeros here that I've not added, but yeah. And then that one. So I don't know if that's what you are getting, but 1, 0, 1, 0, 0, 1, 0, 1. Yes, so at least I'm seeing Paul's submission is similar to mine. But when you don't write, you don't really write the these zeros here in your answer, you know. But if we were converting back, you would need them. But that's I think is quite easy for everyone to remember, to understand. Okay, so how many bits convert A? So that is the question. How many bits are these? So we remove this. So we can say 2, 4, 6, 8, 9. Yeah, so you can take it as 9 bits. Now I'm seeing that we have just a few minutes. Let me just go through BCD code before we leave the codes, because this is the last one. Now, what we've been doing, when we express a number in its binary code, we call it straight binary coding. So if I for example, say that I have a number 10 and I express it as 1, 0, 1, 0. I have a number 7, I express it as 1, 1, 1. I have a number 4 and I express it as 1, 0, 0. This is straight binary coding. And we were doing this using our repeated division or using the other method that we looked at earlier. But in binary coded decimal, if I give you a decimal number like this one, now you see 943, you just find each of these positions binary equivalent and you express it as that. So you have 943. Let's do a smaller number. Let us do something like 67. If we were doing that's too big. Let's do 23. If we were doing 23 base 10, if we are doing straight binary, it is 23. It will be 23 over 2 which is 11, remainder 1, 11 over 2, which is 5, remainder 1, 5 over 2, which is 2, remainder 1, 2 over 2, which is 1, remainder 0, and then 1 over 2, which is 1, which is 0, remainder 1. So you would have 1, 0, 1, 1, 1, base 2. But with BCD, 23 becomes that. We know that 2 is 0, 0, and so BCD uses 4 bits, as a matter of fact. It is 0, 0, 1, and 0, and with 3, it is 0, 0, 1, 1. So we would end up with something like 0, 0, 1, 0, 0, 0, 1, 1. And of course, you can ignore this one. But what the difference I wanted to show you is that 23 in straight binary is actually 5 bits. But 23 in BCD is actually 8 bits. But of course, we can even ignore these last two since they are both zeros, we would still end up as 6 bits. In other words, BCD code is not equivalent to straight binary code. So you see here like 9, you just go get its binary code equivalent. Code is 1001. 4, its binary code is 011, and so on and so forth. This is really easy for us to use, and it is easy for the computer also to use. This is BCD. BCD is binary coded decimal. So it means we only apply BCD on the decimal codes, which are from 0 to 9. Okay, so our BCD codes will range from 0, which its equivalent binary code is 000, to 9, whose equivalent binary code is 1001. Now, what happens to the 110, 10 to 1111? These ones are never used when we are dealing with BCD. These ones are never used because obviously they don't equate to any binary number. And we call these forbidden code groups. So if I tell you that convert something and you find that there is a forbidden code group, you really cannot convert it. And it's just best to mention that there is a forbidden code group that is not. Let me just give a little bit more explanation. I'm finding my computer quite slow this morning. And so we really have our decimal and BCD code. And we have 0, which is 000, 1, which is 0, 2, which is 0010, 3, which is 0011, 4, which is 0100, 5, which is 0101, 6, 0110, 7, 0111, 8, 1000, 9, 1001. Now you see, this is where BCD stops. But if we were doing combinations of 4, there are still combinations of 4 ranging from 1010 all the way to 1111, which have not been used, and we call these the forbidden code groups. So basically, if I give you a number like 75, maybe 875, you just come and get 1000. Everyone just get its equivalent 0111 and 0101, and you have your BCD code. But if we were to need for 875, I think we would have to look at 2 to the power 10, which gives us 1024. 2 to the power 9 gives us, I think, 512. So we would need 10 bits to do straight binary. So straight binary would cost us 10 bits. That with BCD, actually 875 is expressed in 12 bits. So the two are not the same, but they all have their application areas. Okay. Maybe I've explained the forbidden code groups. I'm really sorry about my internet, and hopefully now you got it, because I've used I've talked about forbidden code groups. So these are the code groups beyond 9, which are still combinations of 4, but that we actually cannot use when we consider 10 up to 1111. Those ones should never be. So for instance, if I say what is the BC, if I give you a BCD code, like 1 0 0 0 1 1 0 1 0 0 1 1, and I tell you this is BCD, what is the decimal equivalent? You come and look at 4 groups, start from the lowest significant side, create another 4 groups, and another 4 groups. If you look at 1000, that's 8. If you look at 0011, that is 3. If you look at 1101, this one is not equivalent to any decimal number. So this is a forbidden code group, and it should not appear. And so really this, you cannot convert it back to decimal. All right. I want to end here, but maybe before I end, you do this number for me. Okay. I have a couple of, just do this number for me and then tell me the answers, and then we can call it a day. So it is 137 in binary. So if we do 137, it is 1. I'm going to do the BCD code 1. You do the one for binary. 3 7. This is 0 1 1 1. 3 is 0 0 1 1, and 1 is 0 0 0 1. So you end up with 1 0 0 1 1 0 1 1. Abe Masiko, can't you help us? I give you, I don't know, I give you the recording. So I don't know how these slides that I write in would help you, honestly speaking. I honestly don't know how these slides would help you. Okay, I'm seeing 1 0 0 0 1 0 0 1. Okay. And these are actually 9, but if we were not lucky that these were zeros, we would end up with 12 bits here. Whereas here we have, but what's important is here is for you to see that these two are not equivalent. And so straight binary coding and BCD are not exactly the same thing, but they all have, and we will be using this from time to time. If I have my information coming from the computer, this computer could be some embedded systems, and I have a display, like a calculator, for instance, or any kind of display, I can just convert these values straight from binary into I use BCD, binary to decimal, binary to decimal, and I just write it here, 137, instead of suffering converting from binary back to decimal. So the recorded, yeah, thank you guys. So the recorded slides, I don't see how they help you since I give you the videos and the recorded slides are in there. I don't see what you are going to read from my are written in slides. Also, if you see these slides, for instance, there's nothing in here. It's just a word here, a word there. And we are really working. We are trying to create, I don't want to write everything for you in the slides because you have the book. An advantage of BCD over binary, not so much, other than making it easier for us to convert things from binary to decimal. Because you see with BCD, you just look at the binary number and get its decimal equivalent. So it's easier to convert and display for us human beings. But we need to remember that always the computer will use binary. It does not use BCD, does not use hexadecimal, it always uses binary. Okay. Thank you. Let's stop here. Have a nice week. We are going to meet again on Wednesday. I'll see you then.